Section 3.1, Part 1. So this unit, the main concepts covered are the law of conservation of energy, which is very similar to the law of conservation of mass, potential and kinetic energy, local and global impacts of energy transformations from technology. Key concepts are here for you. I basically just went through them, but feel free to pause here and copy these down if you don't already have them complete. So concept number 1, energy can produce change in a system. So this is page 200 in the textbook. So what is energy? Energy is present in many forms in the world around us. Below are some images showing some types of energy. Which ones do you recognize? First off, this is about page 150 in your notes. You should have already done your key terms for this section and hopefully came across some of these terms and different forms of energy already. So the images show a ton of different forms of energy. Take a moment, pause, and see if you can classify these into the different types. If you don't know what an image is showing you, then skip it and move on to another image. We're going to go through these together now. So energy is defined as, in physics, the ability to do work. So basically to do something with that energy. So if we look at our first example here, this is an example of electricity. A flashlight would be an example of light energy, which is better known as radiant. Music is sound. And we have other examples of sound. So obviously electric energy converted into sound energy. A jack in the box also makes a sound as it pops out. The jack in the box also has a spring involved in its system to pop up out of the box. This is an example of elastic energy. The sun is an example of radiant energy, but as well as nuclear energy. Fission and fusion are the reactions that occur in the sun, and we use the power of fission on Earth to produce energy from radioactive particles. Gasoline and food are used to power either a car, and food is used to power our cells. So what happens is this is an example of chemical energy. So we talked about cellular respiration happening within cells and also combustion reactions which happen in cars. Planes and cars use kinetic energy, which is the energy of motion. We've got a heater. This would be thermal energy. A rock sitting above a ground with the potential to fall is what we call potential energy. Okay, so scientists have investigated energy and discovered several properties of energy. These are key things for us to focus on. So, energy can cause change in a system. For example, energy in the form of heat can change snow to rain. So we see the result of the addition of heat energy in the melting of the snow. There are different forms of energy with different characteristics. Example, radiant energy, which is light, is different from sound energy. So the official name for light energy is radiant energy, and this is because it includes that are not in our visible light spectrum. These forms of energy can be transferred or transformed. So for example, chemical potential energy in a battery can be transformed into light So from one form of energy to another, nothing is locked into one form. Different physical quantities contribute to different forms of energy. So for example, the mass and speed of a ball will influence how far you can throw it. And this is mechanical kinetic energy. So looking at mass and speed as physical properties, these will impact how far the ball can be thrown. And this is based on the amount of kinetic energy that the ball receives. So suppose you were a scientist trying to study a newly discovered form of energy. What are some of the challenges you would need to overcome? How would you observe energy? How would you make observations? What kind of tests would you do? So there's no wrong answer here. We have some examples of what has been done down at the bottom. A few of the examples are shown. Obviously, some of them are beyond the scope of the course. This is like university level, research level examples of how to study this. But there are a few things to think about. What are the problems with energy? Can you see energy, and how easy is it to measure? So even though you can feel something, say heat, how do you actually quantify it? How are you going to observe things? How are you going to make your own observations? What tests are you going to do? How are you going to record that information given what we know about energy in general? Take a few minutes to think about this, and on the next slide, I'll show you a sample answer. Again, no wrong or right answers. Because energy has no mass, it's difficult to observe. And we would need an instrument to measure it, or we would need to observe how energy acts on something. So for example, like a photographic plate being exposed by radiation. So energy systems play an important role here. A system can be defined as anything that is under observation. For example, a bungee cord and a person using the bungee cord would be considered a system. So that's what the image is in the bottom there. So basically, it's what we're looking, seeing, hearing, all of those kind of senses, because this is how we make observations. Make note that a system is something we define, and different people may have different perceptions of what should be included in a system. For example, would you decide to include a bridge when describing a system for a bungee jumper? So this is obviously a yes or no, depending on your opinion of whether or not the bridge should be included. You might say yes, or you might say no. There's no wrong answer. Both are completely valid. You just need to define what you are including in your system when you are describing it and doing any relevant calculations. Can you think of other examples of systems? So other types of systems outside of your bungee cord example, so basically anything you want to think about that is using energy in some way, shape, or form, ensuring you are defining it under the parameters that you see fit. So take a moment and think of some examples. To get you started, here we have a thermos. You would be heating the food to put into the thermos, and that thermos would be considered our system. Yeah, so take a moment, see if you can come up with something else, and then I'll give you some kind of prompts to get you started on that. So pause here, think, and then I will go through this with you. So another example could be something like a cup of hot coffee. I'm observing the cup. I can feel the thermal energy moving off of it and going into the surroundings. There's also matter coming off of it in the form of steam. A computer or phone. Chemical energy in the battery is transformed into different forms of energy, i.e. the computer fan. Chemical to kinetic energy, some sound energy, chemical to light energy, which is radiant, in order to see the screen. A couple of more examples, a microwave. You could think of the process of heating up food before you put it into the thermos as being an example of a system, boiling a pot of tea, and then something like driving a car could also be a system that you could observe. Everything else in the universe that is not included in the system is considered the surroundings. In the case of the bungee jumper, the surroundings would be the sky, trees, other people nearby, cars, etc. So anything that is in the universe that is not part of our system that you are observing, so you can stretch your surroundings as far as you wanted to when describing them. If you thought of other systems other than the ones that I described for you, you would also want to think about those surroundings. So going back to the thermos example, we could talk about the surroundings as being on the counter, the stove, or anything that you might want to possibly include in that previous photo and beyond. For our coffee cup system, the surroundings would be something like my desk, the chair, the room, the school, etc. For the computer, it could be the power cord, the desk, a plug, a notebook, your room, the house, your city. So you can extend this out as far as you choose. So just filling in what we had before. Our equation we use to talk about the universe is equal to the system plus the surroundings. So that's literally everything. You've got your system and your surroundings, and together they make up the universe. You can isolate that down as small as you want, depending on how vague you want to be. So let's look at an example of water molecules. So our system could be the water or the ice, and the surroundings would be everything else. So the cup is being held in air, that's around the table, that you, the observer, are walking by. Okay, so take a moment to think about this. Make sure you understand kind of the fact that you define the system and the surroundings. It's all how you choose to observe it and lay it out. But you should know that this formula, the universe is equal to the system plus the surroundings. Okay, and this is the end of part 1.